Hello, and welcome to the Quiet Cosmos. Tonight the whole evening is spent going straight up, away from the ground, away from the planets, away from every familiar direction, just up and up and up again. A simple question sits underneath the whole route. Leave the solar system behind by climbing straight up from it, and eventually leave the galaxy behind too, straight up from that as well. Are those really the same direction? They are not, and the difference between them turns into most of tonight's story. One climb is almost nothing, gentle and short, managed decades ago by ordinary machines, while the other climb has never once been attempted by anything human hands have built. If a slow climb straight up through cosmic scale is the kind of company that helps a mind unwind at the end of a long day, a quiet like or a subscribe helps this small channel reach more of the people already searching for exactly this kind of quiet science. It costs nothing more than a moment, and it is the only thing this channel will ask of you tonight. Tonight's route starts close to home, inside the flat spinning plane that already holds every planet in the solar system, and only slowly widens outward toward the far larger, far flatter plane that holds the whole galaxy around it. So settle in, let the evening grow slow and heavy, and follow that plane outward, one quiet layer at a time, from a familiar disk of planets toward something built from hundreds of billions of stars. Almost every large body inside the solar system keeps to one shared flat plane, rather than scattering off in random directions around the sun. The 8 planets sit inside it, and so do most of their moons, and so does the broad ring of rubble known as the asteroid belt. Look at a scale model of the solar system, and the flatness becomes obvious almost immediately. Nothing sprawls up or down by very much at all. A handful of smaller, icier objects wander further from that plane than most. But the big, familiar bodies hold their place inside it with real discipline. Whatever built this system favored one direction of travel far more than any other. And even the outermost reaches of the system, far past the last planet, mostly continue the same pattern, rather than breaking into some wilder arrangement. A visitor arriving from far outside, with no prior knowledge of the Sun's family, could plot the position of every major body and notice the same flat habit repeating itself almost everywhere it looked. Flatness here is the norm. Home looks less like a scattered handful of crumbs and more like one wide, quiet dinner plate, spinning gently around a bright center. That shared plane has a name, the ecliptic, drawn from the slow path the sun appears to trace across Earth's sky over the course of 1 year. Ancient skywatchers noticed that path long before anyone understood why it existed, tracking the sun's yearly drift against the fixed backdrop of stars. What they were really charting, without realizing it, was the flat, plain Earth's own orbit carves through space. Every other planet's orbit gets measured against that same line today, the ecliptic serving as the reference plane astronomers still return to first, chosen mostly for convenience rather than for anything special about the geometry itself. Modern star charts still print this same line across published sky maps, guiding where telescopes point and how positions get recorded for anything orbiting nearby. Even instruments launched centuries after those first sky watchers still orient themselves against that very same slow, ancient path. Still, the measuring stick belongs to one planet in a family of many, the one doing the measuring. Individual planetary orbits lean away from that shared plane by only a small amount. Earth's orbit defines the ecliptic outright, by definition, so it cannot lean away from itself at all. Every other planet drifts from that reference by a modest few degrees, never by anything close to a right angle. Uranus and Jupiter sit closest to level, their orbits practically painted onto the same flat sheet as Earth's own, while Neptune and Mars tilt a little more, and Venus leans further from that sheet than any other planet except Mercury. None of those tilts, added together, would make the solar system look anything but flat from a distance. Pluto and the smaller icy bodies drifting far beyond Neptune lean further from that shared sheet than any planet does, Pluto itself by some 17 degrees, and even they still trace their own wide loops around the same bright center. Small departures, stacked politely one after another, still add up to something the eye would call level. Mercury holds the record for the steepest tilt of any planet in the solar system, leaning away from the ecliptic by about 7 degrees, according to NASA figures. 7 degrees sounds small on paper, and against the sweep of a whole solar system, it truly is. Stand 2 flat sheets of paper almost on top of each other, nudge one corner up just slightly, and the mismatch barely registers unless someone is looking for it. That is roughly the scale of Mercury's lean, compared with the shared plane the other planets keep. Only Venus, at a little over 3 degrees, comes close to half of that departure. Its tilted orbit still carries Mercury back through roughly the same plane every single time it circles the Sun, never wandering far enough to break the family habit completely. Even the planet with the loosest grip on flatness still keeps that grip fairly tight. Mercury bends the rule further than any other planet manages, and even that bend stays small enough to leave the rule holding almost everywhere. That shared flatness goes back to the very birth of the solar system, to a slowly spinning cloud of gas and dust that gradually pulled itself inward under its own gravity. A cloud spinning in open space cannot collapse evenly in every direction at once. Rotation resists being squeezed along its own equator far more than along its poles. So the cloud kept collapsing straight down along its spin axis, while spreading outward along its spin, the same way a slowly turning skater's arms sweep wide while the body itself stays upright. What began as a roughly spherical cloud settled, over time, into a broad, thin, spinning disk. Everything that later formed inside that disk, planets included, inherited its shape almost automatically. Astronomers can watch versions of this same collapse happening right now, in telescopes pointed at younger stars, still wrapped in their own swirling disks of gas and dust. Every one of those distant disks looks remarkably similar, flat and wide, suggesting the young solar system likely looked no different once. Given enough time and enough spin, a shapeless cloud of gas tends to iron itself nearly flat. Everything that circled the young sun inside that flattened disk of leftover gas and dust naturally settled into roughly the same plane as everything else nearby. Material drifting even slightly above or below the disk kept crossing paths with material inside it, and each crossing traded a little energy and a little momentum. Those countless small collisions, repeated over millions of years, gradually herded stray particles back down toward the crowded middle layer. Anything that refused to settle mostly got flung away or swallowed, rather than staying stubbornly tilted. Order, in this case, came less from any single rule and more from sheer repetition. Even material that started out on a fairly steep, tilted path tended to lose that steepness gradually, nudged flatter with every additional pass through the crowded middle. Ordinary physics, repeated patiently enough across a stretch of time longer than the solar system has existed in its finished form, did all of the sorting on its own. Enough gentle nudges, applied patiently enough, taught almost every wandering particle the same flat habit. Astronomers also lean on a slightly different reference than the ecliptic, called the invariable plane. calculated from the combined angular momentum of the entire solar system, rather than from Earth's orbit alone. Every planet's mass, speed, and direction of travel feeds into that single calculation. The result is a plane that reflects the system as a whole, not just the habits of one particular world. It shifts only very slightly if a planet's orbit gets measured a little differently, which makes it useful as a steady baseline. Earth's ecliptic remains the more familiar reference, the one taught first and used most often in everyday astronomy. Mission planners occasionally reach for this steadier reference when plotting long, complicated trajectories that need to hold up across many years, rather than relying on a single planet's yearly path. It offers a kind of quiet, unglamorous second opinion, built from the whole family rather than from any one member of it. Still, the invariable plane offers a quieter, more democratic way of asking the same basic question. Which way is flat, really? The invariable plane and the ecliptic sit remarkably close to one another, separated by only about 1.5 degrees according to NASA, a gap small enough to lose inside the width of a finger held at arm's length against the sky. For most practical purposes, and certainly for tonight's purposes, the two planes can be treated as one and the same flat sheet. Different methods, different starting assumptions, and yet almost the identical answer falls out at the end. Small disagreements like this one tending to reassure scientists rather than worry them, since independent methods rarely agree this closely by accident. A gap this narrow would be almost impossible to notice just by looking upward on any given night, even for someone deliberately searching for it. Precision instruments, not casual eyesight, are what eventually revealed just how closely the two calculations agree. Two separate ways of asking the question, and the sky gives back almost the same answer either time. Step back far enough from that shared plane, high enough to look straight down on the whole solar system at once, and the picture changes completely. Up close, orbiting bodies look like a busy scatter of dots, each one following its own private path. From a great height directly above, those same dots resolve into something closer to a thin, spinning disk, bright at the center and thinning out toward the edges, only the vantage point having changed rather than the motion itself. The planets stop looking scattered and start looking organized, all of them tracing rings within rings across the same flat sheet. Photographs taken by spacecraft looking back toward the inner solar system from unusual angles have actually captured glimpses of exactly this effect. Planets lining up along one visible band rather than scattering randomly across the frame. Distance turns chaos into shape, the same way stepping back from a crowd turns separate people into a pattern. That thin, spinning disk is home. Every planet, every moon, nearly everything solid enough to name, riding together inside one shared, flat plane around a single star. Leaving it means choosing a direction, and the simplest direction of all is straight up, directly away from that crowded sheet rather than sideways along it. Keep climbing in that direction, past the orbit of the outermost planet, past the thin scatter of icy debris beyond it, and the question naturally becomes, what actually waits up there? Not sideways, not around, but straight up and away from the plane itself. That climb needs no real speed, only patience and a willingness to keep moving in one steady direction for a very long time. Everything from this point forward follows that same single upward line, one quiet step further from the crowded disk left behind. That single direction carries the whole of tonight's slow climb, one flat layer giving way to the next. The plane of the planets is not the only flat spinning disk nearby. The Milky Way itself is built the same way, a broad wheel of stars, gas, and dust, turning slowly around its own distant center. Zoom out far enough from the solar system, and the same basic shape reappears at a much larger scale. Just as planets settled into one shared sheet around the Sun, the galaxy's own stars settled into one shared sheet around its center, for very similar reasons. Two structures, two very different sizes, and yet the same patient flattening at work in both of them. Both wheels spin for the same underlying reason too, each one built from a great deal of scattered material that gradually pulled itself together under its own gravity over spans of time too long to picture directly. Neither structure needed anyone to design it. Ordinary gravity, given enough time, kept arriving at the same flat answer. Small disk, big disk. One habit repeated at wildly different scales. The galaxy's own flat plane carries a name of its own, the galactic plane, and it is marked out across the sky by a dense, continuous band of stars wrapping the whole of it. Step outside on a clear, dark night, far from city light, and that band becomes visible as a pale, textured stripe stretching from horizon to horizon. Every star inside that stripe sits roughly within the galaxy's own flat disk, seen edge-on from a spot well inside it. Far from any illusion or trick of the eye, the stripe is a direct physical view of a real structure. That same band has guided travelers and storytellers for thousands of years, long before anyone understood it as a disk of stars seen edge-on rather than some separate, softly glowing cloud overhead. Cultures scattered across the whole planet gave it their own names, usually describing it as a river, a road, or a spilled trail of something bright. The galactic plane is simply the flat sheet that stripe traces across the whole sky at once. The plane of the planets and the plane of the galaxy are not the same flat sheet tilted at some shared angle by pure coincidence. They lean against each other instead, two separate planes set at a real angle to one another, like two plates propped against a table at different slants. Standing inside the flat plane that holds the planets does not automatically mean standing inside the galaxy's own plane as well. One is a small, tidy disk built around a single star. The other is a vastly larger disk built around the combined pull of hundreds of billions of stars. Neither plane defers to the other. Each one simply describes the flat habit of whichever structure built it, at whatever scale that structure happens to occupy. A traveler moving between the two has to keep track of two separate flat references at once, not one shared one. Different sizes, different builders, and only a partial overlap in the direction each one happens to face. The angle between the ecliptic and the galactic plane comes out to roughly 60 degrees, according to NASA figures. That is closer to a right angle than to anything resembling parallel. A gap that wide means the two planes barely share a direction at all. Tilt one sheet 60 degrees against another, and the two barely touch except along one thin line. The solar system's formation never lined it up neatly with the wider galaxy surrounding it, since the two structures simply formed on their own separate schedules, at their own separate angles, without consulting one another. Earlier generations of astronomers, working only from careful, naked-eye positions, still managed rough versions of this same measurement centuries before modern instruments confirmed it precisely. Their early estimates pointed toward a wide, stubborn gap between the two planes, long before anyone had the tools to pin the exact number down. 60 degrees of disagreement, quietly written into the sky, waiting for anyone patient enough to measure it. because of that steep 60-degree tilt. Straight up from the flat plane the planets share does not point toward the galactic pole at all. It points off at a sharp angle instead, one that actually runs closer to the galaxy's own crowded disk than away from it. A traveler leaving the solar system straight upward, expecting a clean shot toward open galactic space, would instead be climbing at a shallow slant across the Milky Way's own busy plane rather than straight out of it. That mismatch surprises most people the first time they hear it described plainly. Up, in other words, depends entirely on which flat sheet is doing the defining. Anyone planning a journey straight upward from the solar system, expecting a quick escape into open galactic space, would need to correct for this mismatch first. Ignoring it would mean crossing far more of the crowded disk than necessary before finally rising clear of it. Two different planes, two different meanings for the very same word. Astronomers work out that tilt by comparing two fixed points on the sky. The North Pole of the ecliptic, sitting directly above the planet's own shared plane, and the North Galactic Pole, sitting directly above the disk of the Milky Way. Each pole marks the single direction perfectly perpendicular to its own flat plane. Measuring the angular distance between those 2 points on the sky gives the tilt between the two planes directly, without needing to measure either plane itself. It is a clean piece of geometry built on careful star charts assembled over centuries. Once both poles are pinned down precisely, the angle between the two planes practically falls out on its own. Neither pole sits near any bright, obvious landmark visible to the naked eye. Both had to be worked out mathematically before anyone could ever point a telescope directly at either one. Star charts refined over generations eventually pinned each pole down to a precise, repeatable coordinate. 2 dots on a map, and a whole geometric relationship follows. Those 2 poles sit far apart on the sky, one inside the constellation Draco and the other inside the constellation Coma Berenices. Draco winding across the northern sky as a long, faint chain of stars, while Coma Berenices sits as a quiet, scattered patch nowhere close to it. Anyone tracing a line from one constellation to the other would cross a wide stretch of open sky along the way, the same 60-degree separation drawn out visually instead of stated as a number. 2 poles, 2 very different neighborhoods of the sky, standing in for 2 very differently tilted planes. Neither constellation appears especially bright or dramatic on its own. Both are quiet, easily overlooked patches of sky that a casual stargazer could spend years studying without ever suspecting either one carried any real geometric importance. Distance on a star chart here is really just an angle wearing a different disguise. No one designed this tilt on purpose. The solar system formed by spinning in whatever direction its own small local cloud of gas happened to be turning at the time, with no reason at all to line up neatly with the much larger galaxy surrounding it. A slightly different starting spin, billions of years ago, could easily have produced a completely different angle today. Chance, not design, decided which way the young solar system's flat disk would eventually face, since the wider galaxy had set its own direction long before the sun's own small cloud ever began collapsing. A marginally different clump of gas, or a slightly different early nudge, could just as easily have tilted the young system the opposite way instead. It simply happened to land where it landed. One random spin, locked in early, still shapes which way is up from here. Most nearby stars share the same basic mismatch. Any planets circling those stars, if such planets exist, sit inside their own small flat plane. And that plane tilts against the galaxy's own disk by its own separate, essentially random angle. No shared rulebook forces every stellar system to line up the same way. Each star's local cloud spun however it happened to spin when it first began collapsing, long before anyone was there to compare it with its neighbors. Multiply this one solar system's mismatch by the hundreds of billions of stars scattered through the galaxy's disk, and a whole galaxy's worth of independently tilted little planes appears. Astronomers studying planets around other stars now have to account for this same mismatch whenever they try to compare one system's flat plane against another's. No universal alignment ties any of these separate little disks together into one tidy, shared orientation. Every stellar neighborhood quietly facing its own private direction. The planet's own plane, then, is itself a small, tilted disk, riding along inside a far larger, flat disk, and leaning against it rather than lying flush inside it. A small dinner plate, propped at an angle inside a much bigger, wider bowl, carries roughly the same idea. That small plate still moves together with the bowl, carried along its slow overall rotation, even while keeping its own separate lean. Nothing about that inner tilt stops the solar system from orbiting the galaxy's center the way every other star does. That inner lean means the flat disk of planets never presents its full face directly toward the wider galaxy. It always shows something closer to an angled edge instead. Anyone picturing the solar system from far outside would see a small tilted saucer, caught mid-spin, riding inside something enormously larger. Small and tilted, big and flat, one riding quietly inside the other. From this point forward, up means one specific direction, straight out of the galaxy's own flat plane, tilted at that same steep angle, close to 60 degrees, away from the shallower plane the planets keep. It is not the same up a person standing on Earth might casually picture, tracing a line straight through the ecliptic and out past the planets. It is a bigger, steeper, more deliberate direction. That difference matters because so many casual descriptions of leaving the solar system quietly assume the two directions are the same, when they are not. One direction, fixed for the night, carrying everything that follows. Climb out of the plane of the planets along that redefined direction for long enough, and the view stops being about leaving the solar system at all. Early on, the planets shrink behind a traveler the way any familiar neighborhood shrinks behind someone driving away from it. Keep going, though, and the whole framing changes. The sun becomes just one more star, and the wider galaxy itself starts coming into view from outside its own crowded disk. What began as an exit from one small system slowly turns into a view of a much larger one, seen properly from the outside for the first time. The direction itself never changes partway through the climb, only the disk does, growing harder to see star by star and easier to see as one broad glowing hole the further the climb continues. What started as a departure slowly becomes something closer to a portrait, the meaning of the journey shifting one quiet threshold at a time. The disk of the Milky Way is not one single uniform plate of stars. Astronomers actually split it into two separate layers, nested one inside the other, the way a thin sheet might sit on top of a thicker cushion underneath it. Each layer holds its own distinct population of stars, with its own age, its own thickness, and its own general shape. Seen from a distance, the two layers blend together into what looks like one continuous disk. Look closely enough, star by star, and the seam between them becomes clear. That same two-layer structure shows up, in rough form, in plenty of other spiral galaxies studied from a safe distance, suggesting nothing especially unusual about how the Milky Way happened to organize itself. Astronomers first suspected the split from patterns in stellar motion long before anyone could separate the two populations directly by eye. One disk, on closer inspection, is quietly built from two. The thinner of the two layers carries the name thin disk, and it holds the galaxy's younger stars, along with nearly all of its gas and dust. Most of the raw material still available for building new stars sits crowded into this one narrow layer. Older stars exist here too, scattered among the newer ones, but the balance tips heavily toward youth compared with the layer wrapped around it. Anything actively glowing, actively forming, or still surrounded by its own birth cloud tends to live inside this thin disk specifically. It is the busiest, most active layer of the whole structure. Astronomers estimate that a large share of the galaxy's total stellar mass sits inside this one relatively thin layer, packed closely enough that whole star-forming regions can be found glowing within it on any given clear night. Step outside this narrow band, and both the raw material and the finished stars grow noticeably scarcer almost immediately. Most of the galaxy's real work of building new stars gets done down here. The thin disk measures roughly 1,000 light-years from top to bottom, according to NASA estimates. Set beside the galaxy's overall width, somewhere near 100,000 light-years across, that thickness looks almost paper-thin by comparison. The same wide, flat shape keeps reappearing at every scale tonight, far wider than it is tall. Nearly every familiar star pattern visible from Earth sits within that same thickness. Thin, in this context, is a genuinely relative word. 1,000 light-years still holds room for billions of stars. A traveler shrinking the whole galaxy down to the size of an ordinary dinner table would find the thin disk barely thicker than a sheet of paper laid flat across it. That kind of scale model helps explain why astronomers so often reach for the word thin without hesitation. Flatness on this scale still leaves room for crowds beyond counting. Nearly all star formation across the whole galaxy happens inside this one narrow layer. Clouds of gas and dust need real density to collapse under their own gravity and ignite as new stars. And that density only builds up where material stays crowded closely together. The thin disk supplies exactly that crowding, concentrating gas along a narrow band instead of spreading it thinly across a much larger volume. Step outside that band, into the thinner material above or below it, and the raw ingredients for new stars grow scarce fast. Telescopes surveying the thin disk regularly catch fresh examples of this process midway through, glowing stellar nurseries lit from within by newborn stars still wrapped in the very gas that built them. New stars keep choosing the same crowded neighborhood their predecessors chose before them. The galaxy's spiral arms live inside this same thin disk, broad, bright bands of young, hot stars that give the Milky Way its familiar pinwheel shape when viewed from outside. Seen from a great distance, those arms would trace loose, sweeping curves, winding slowly outward from the crowded center. Up close, from inside the disk itself, the arms mostly show up as slightly denser stretches of young stars and glowing gas along an otherwise ordinary strip of sky. No fixed or solid structure at all. Since stars pass through an arm and continue onward rather than staying locked in place forever. The pattern itself moves more like a slow rolling wave than like a rigid spoke. Radio telescopes, better suited than ordinary optical ones for peering through the galaxy's own dust, have helped astronomers trace the rough outline of these arms even where visible light cannot reach. Each arm blends gradually into the next, rather than ending along any sharp, clean edge. The shape survives from motion alone, built by nothing that ever stands still. Stars belonging to the thin disk travel on orbits that stay close to flat and close to circular, rarely straying far above or below the galactic plane along the way. Each orbit loops around the galaxy's distant center in roughly the same direction as its neighbors, all of them moving together in an orderly, coordinated sweep. Little vertical wobble interrupts that motion. A thin disk star mostly stays where it started, height-wise, orbit after orbit. That discipline is part of what keeps the thin disk thin in the first place. Order among individual stars adds up, collectively, into order across the whole layer. Astronomers can measure this discipline directly by tracking the individual motions of thousands of nearby stars, watching how little each one strays from its neighbor's shared level path. The pattern holds remarkably well across enormous stretches of the disk, not just in the small patch of sky near the sun. Millions of separate paths agreeing to stay level. The sun itself counts as a thin disk star, born inside this same layer of gas, dust, and young stars roughly 4.5 billion years ago, condensing out of the same crowded neighborhood of raw material as countless other stars forming nearby at around the same time. It settled into the same kind of flat, fairly circular orbit that most thin disk stars share, and billions of years later, that orbit still keeps the sun close to level, moving in step with the layer that raised it. Home, in other words, sits well inside the busiest, youngest part of the whole galactic structure. Plenty of other stars scattered nearby share almost the exact same birth story, condensing from the same generation of collapsing gas clouds before drifting slowly apart from one another over billions of years. The Sun's own particular birth cluster has long since dispersed, its members scattered across a much wider stretch of the disk. One ordinary star, born in the crowd, still traveling with the crowd today. The thin disk carries so much dust that looking along it, whether toward the galactic center or away from it, means looking through a long, dim tunnel of material rather than through open, empty space. Light from distant stars has to fight its way through that dust the entire time, losing brightness and shifting color along the way. Astronomers call this effect extinction, and it thickens the closer a line of sight stays to the crowded galactic plane. Entire regions of the galaxy stay hidden behind that same haze, no matter how powerful the telescope pointed at them. Distance alone does not explain how much of the galaxy remains unseen from here. Direction matters just as much. Interstellar dust of this kind is made from tiny grains, smaller than a single grain of sand, yet spread across such enormous distances that their combined effect becomes overwhelming. Infrared and radio instruments, built to see past visible light entirely, remain the main tools astronomers use to look straight through it. Dust, patient and thick, blocks more of the view than distance ever could on its own. Looking straight up, out of the thin disk entirely, offers the shortest possible path through all that dust. A line of sight along the crowded plane can cross tens of thousands of light years of haze before reaching open space beyond it, while a line of sight straight up, by contrast, only has to cross a few hundred light years of the thin disk's own narrow thickness. Short trips through dust lose far less light than long ones, which makes the view upward noticeably clearer than the view sideways. And straight up ends up being the one direction where the dust simply runs out fastest. astronomers studying the earliest, most distant galaxies specifically favor targets lying near this cleaner upward direction, since a clouded, dust-choked line of sight would blur or hide the faintest, oldest light almost completely. And clear sightlines in this part of the sky are rare enough to be treated as a genuine resource. The shortest road through the haze happens to point directly overhead. That same clear path helps explain why astronomers often study distant galaxies by looking out through the poles of the Milky Way's own disk, rather than along it. Pointed sideways, a telescope has to fight through the thickest dust and the most crowded starlight the galaxy has to offer. Pointed straight up or straight down, the same telescope gets a comparatively open, uncluttered window onto the universe beyond. Some of the deepest images ever captured of the distant universe were deliberately pointed through exactly this kind of clear polar gap, avoiding the thick dust and crowded starlight closer to the plane entirely. Choosing the right direction can matter every bit as much as building a bigger telescope. The busiest layer of the galaxy still leaves one tidy doorway open, directly overhead. The thin disk is not the only layer sitting above and below the galactic plane. Wrapped loosely around it sits a second layer, older and considerably puffier, spreading further above and below the plane than the thin disk ever does. That second layer holds a different population of stars entirely, with its own separate story about how it came to exist. Nothing about its outer edge is sharp or clearly marked. The two layers blend gradually into one another, rather than meeting at any hard boundary. Climbing straight up from here eventually means passing out of one layer and into the next. Astronomers first suspected this second, puffier layer existed by noticing a small population of stars whose motion and chemistry simply did not match the tidy, youthful, thin disk surrounding them. Only later, with better instruments, did that suspicion firm up into a properly separate, well-measured structure. One disk, thin and busy, gives way slowly to something older, quieter, and considerably thicker. That second, puffier layer carries the name thick disk, and it is made up almost entirely of old stars, with very little gas or dust left inside it to build anything new. Whatever raw material once filled this layer has mostly been used up or scattered long ago, leaving little behind for fresh star formation. New stars essentially stop forming here, not because the layer lacks room, but because it lacks the right ingredients. Almost every star counted inside the thick disk is old, quiet, and long past whatever active youth it once had. Astronomers can pick these stars out fairly reliably just from their motion and their chemistry, without needing to see the layer as a separate structure directly. Even scattered individually among younger neighbors, a thick disk star tends to stand out once its orbit and its makeup are properly measured. Call it a retired neighborhood, standing right next to a much busier one. The thick disk spreads several times higher and lower above the plane than the thin disk manages, extending something like 3,000 light-years above and below it by some estimates, though different studies measure that thickness in somewhat different ways, so the number stays a little soft around the edges. Even the most conservative versions still describe a layer noticeably puffier than the thin disk wrapped inside it, roughly like a wide cushion loosely wrapped around a narrower, flatter sheet, both centered on the same galactic middle. Some surveys measuring slightly different populations of stars, report a considerably taller layer still, which is part of why any single number describing the thick disk deserves a healthy dose of caution, and even the most careful measurement of a structure this diffuse still carries real uncertainty built into it. Puffier, taller, and considerably less crowded, this second layer wraps the whole busy disk in something gentler. Stars belonging to the thick disk formed earlier in the galaxy's history, back when the Milky Way itself was younger, messier, and still settling into the tidy, flat shape it holds today. Star formation back then happened under rougher, less organized conditions than it does now. Clouds of gas collapsed unevenly, orbits came out less polished, and the whole young galaxy carried a rawer, more chaotic character. Stars born during that early, turbulent period still carry the marks of it, billions of years later. Age alone separates the two layers almost as cleanly as location does. Simulations built to recreate the young galaxy's early history tend to reproduce roughly this same picture, a rougher, thicker layer settling out before a calmer, thinner one forms on top of it later. That ordering, thick first and thin afterward, matches what astronomers actually observe today. The galaxy's early residents ended up scattered a little higher and a little rougher than the ones that came later. Orbits inside the thick disk look noticeably less tidy than orbits inside the thin disk. They tilt more steeply against the galactic plane, stray further from a perfect circle, and carry each star higher above and lower below the plane with every single loop around the center. A thin disk star mostly stays level. A thick disk star drifts up and down as a normal part of its regular path. That constant vertical wandering is part of what gives the layer its extra height in the first place. Messier orbits, left over from a messier birth, simply spread themselves across more space. Astronomers measure this untidiness directly by tracking how fast and how far individual thick disk stars move relative to their orderly thin disk neighbors nearby. The gap between the two populations shows up clearly enough that sorting one from the other has become a fairly routine measurement. Height here is really just untidiness written out across 3 dimensions. One leading explanation for the thick disk's puffy shape points to an ancient collision, a smaller galaxy merging with the young Milky Way billions of years ago, stirring up the orbits of stars that were quietly circling it at the time. A gravitational disturbance that size does not politely leave existing orbits untouched. It shapes them, tilts them, and stretches some of them well away from the flat plane they once kept. Traces of that disturbance would still show up today as exactly the kind of thicker, messier layer astronomers actually observe. Other explanations exist alongside this one, including slower, gentler heating processes acting over very long stretches of time. Evidence collected so far tends to favor some version of an early, violent event over a purely gradual one. Similar collisions have been spotted happening right now around other nearby galaxies. Smaller companions slowly being pulled apart and absorbed by a larger neighbor's gravity. Watching that process unfold elsewhere gives astronomers a useful, present-day preview of what likely happened to the young Milky Way long ago. Somewhere underneath its current calm, the galaxy may still be carrying the bruises of a collision from its distant youth. Thick disk stars also tend to carry fewer heavy elements than the younger stars filling the thin disk nearby. Heavy elements, in astronomy, mostly get built inside earlier generations of stars, and then scattered back into space when those stars eventually die. Each new generation of stars inherits a little more of that enrichment than the generation before it. Stars born early in the galaxy's history, before many generations had lived and died, simply had less enriched material available to draw from. That chemical shortage still shows up clearly in the makeup of thick disk stars today. Spectroscopes, instruments that split starlight into its component colors, let astronomers read this chemical history directly from a single star's light, without ever needing to visit it. That same reading lets a thick disk star be sorted from a thin disk one almost as reliably as measuring its orbit would. Chemistry, in this case, works almost like a growth ring inside a tree, quietly recording how early a star arrived at the party. Even at its outer edge, the thick disk still belongs to the same overall rotating structure as the thin disk sitting inside it. Both layers circle the same distant galactic center, carried along by the same underlying rotation of the galaxy as a whole. They differ mainly in height and in speed, not in the basic direction each one turns. A star drifting up into the thick disk does not stop orbiting the center. It simply orbits a little higher and usually a little slower than a star confined to the thin disk below. Two layers, one shared spin, each one riding its own particular altitude within it. A star can, in principle, drift slowly between the two floors over very long stretches of time, gradually shifting from one population's habits toward the others. Most stars, though, spend nearly their whole existence comfortably settled on whichever floor first raised them. Different floors of the same slowly turning building. Climb high enough above the plane, and a traveler would pass first through the crowded thin disk, then through the sparser thick disk wrapped around it, and finally leave both layers behind completely. Beyond that second layer, the crowd of stars thins out dramatically, replaced by a much emptier stretch of space. Nothing marks that final boundary with a wall or a clean edge. The last few thick disk stars simply grow rarer and rarer until effectively none remain. Somewhere past that fading edge, a traveler would be outside the galaxy's disk entirely, no longer riding inside either layer. Two crowded floors, and then, quite suddenly, open air. That transition happens far too slowly for any human timescale. A traveler moving at realistic speeds would spend many thousands of years crossing from one layer into the next. Distance here measured far more comfortably in light years than in anything resembling an ordinary afternoon's walk. The climb from here forward starts leaving the disk itself behind for good. The sun does not sit anywhere near that emptier space above the disk. It orbits deep inside the thin disk itself, close to the crowded plane both layers are built around. One ordinary star among the busiest and youngest population the galaxy has to offer. Straight up from here still means climbing through the full thickness of the thin disk first, and then through the whole puffier span of the thick disk after it. The sun's own position doing nothing to shorten that particular climb. Home sits firmly inside the crowd, not somewhere out past its edge, sharing its immediate neighborhood with an enormous number of other stars, gas clouds, and drifting dust that thins out only well beyond both layers. Every foot of altitude gained from here still has to be earned, one layer at a time. The sun does not sit exactly on the central line of the galactic plane. Like most of the stars near it, the sun rides slightly off to one side of that shared midline, rather than tracing it exactly. A small drift above or below is closer to the rule than the exception among nearby stars. The sun's own offset places it just above that line rather than below it. Astronomers measure this kind of offset using extremely precise positions and distances gathered by dedicated space telescopes, tracking each star's exact location relative to the shared galactic middle. Even a small, steady offset like this one becomes measurable once instruments grow sensitive enough to catch it. Hardly any star in the whole crowd sits exactly on the mark, and the Sun is no exception. Current estimates place the Sun something like 60 light-years above the galactic midplane, based on data gathered by the Gaia Space Telescope. Set against the full thickness of the disk surrounding it, that offset counts as a small one. 60 light-years would carry a beam of light most of a human lifetime to cross, and yet, on a galactic scale, it barely counts as a step away from the middle. Different methods of measuring that height give slightly different numbers, so the figure stays a soft, rounded one, rather than an exact fix. Even so, every version of the estimate keeps the Sun close to the plane rather than far from it. Earlier generations of astronomers, working with cruder instruments, could only guess at this height using indirect methods, arriving at numbers considerably less precise than today's best estimates. A steady, patient survey of the whole sky has narrowed that older uncertainty considerably, without erasing it completely. Call it a small nudge above the middle, not any real departure from it. 60 light-years amounts to a genuinely tiny distance by the standards of the thin disk itself. Something close to 1/16th of its full 1,000 light-year thickness. Scaled down to something more human, that would be roughly like standing 2 meters off-center inside a room 30 meters tall. The Sun's position stops looking unusual once that proportion sinks in. It sits closer to the true middle of the disk than nearly anything else nearby, drifting off to one side by only the faintest possible margin. Being near the plane, in other words, is not a special privilege reserved for a handful of stars. That proportion helps explain why no dramatic consequence follows from the Sun's small offset. Local starlight, local temperature, and local star density are no different for it. A neighbor a little further off to one side would look and feel almost exactly the same from up close. Nearly every nearby star quietly shares that same ordinary condition, the Sun included. That height above the plane does not stay fixed. Like a slow carousel horse that rises and falls even while circling the same track, the Sun drifts gently upward and downward through the disk over the long course of its orbit around the galactic center. Right now, that drift happens to place it a little above the midline. Given enough time, the same gentle motion will carry it back down through the plane and out the other side. Nothing sudden or dramatic marks this vertical wandering. It unfolds slowly, over spans of time longer than any human institution has ever lasted. Astronomers reconstruct this vertical motion by carefully combining a star's current position with its measured velocity, projecting its path both forward and backward through time. The same basic method works for tracking any nearby star's long, slow bob through the disk, not just the Sun's own. Underneath the much larger circular ride sits this quieter, ongoing bob, up and then down again. That gentle vertical drift comes from the combined gravitational pull of every other star and cloud of gas near the Sun's own path around the galaxy. Whenever the Sun strays upward, away from the crowded midline, that surrounding mass tugs it gently back down again. The same pull works in reverse whenever the sun drifts too far below the plane instead. Nothing single-handedly controls this motion. It emerges from the summed effect of an enormous crowd, each member contributing only the faintest nudge. Enough small nudges, added together, behave almost like one steady, patient hand. Remove that surrounding mass, even hypothetically, and the sun's gentle bobbing motion would behave completely differently, drifting away rather than being pulled steadily back. The whole disk, in this sense, behaves like a loose, invisible net that quietly catches anything that strays too far from its center. The whole disk, in effect, keeps gently coaxing every wandering member back toward its own crowded middle. A full cycle of that rise and fall, up from the plane, back down through it, below it, and finally back up again, takes something like 60 to 70 million years to complete. Set against a single human lifetime, that span is almost impossible to picture directly. Set against the age of the galaxy itself, though, it counts as a comparatively short, repeating rhythm, played out again and again over billions of years. The sun has completed dozens of these slow vertical laps in the time since it first formed. Each lap unfolds far too slowly for any single observer to notice even the smallest part of it directly. This rhythm runs on its own separate clock, driven by vertical motion through the disk, rather than by any orbit around the galactic center. Two separate rhythms, moving at two separate paces, and both quietly playing out at once. One long, quiet rhythm, repeating patiently underneath everything else the sun does. Somewhere inside that longer cycle, the sun crosses the crowded midplane itself roughly every 30 to 35 million years. Each crossing carries it briefly through the densest part of the disk, the same narrow band holding most of the galaxy's gas, dust, and young stars. The crossing itself passes quickly, at least on a galactic clock, before the sun drifts back out toward the other side. Nothing catastrophic marks these passages, as far as current evidence shows. The extra material nearby simply thickens for a while and thins again afterward. Astronomers place the sun's most recent crossing of the midplane in the relatively recent past on a galactic timescale, with the next one still tens of millions of years away. Neither crossing has ever posed any obvious danger. The extra density involved remains modest by any measure. 30 million years is a long wait for any single crossing. And yet, over the sun's whole lifetime, it has made this same quiet pass many times over. Between them, the thin disk of young stars, the thicker cushion of older ones wrapped around it, and the sun's own gentle, quiet drift near the shared middle account for almost everything gathered tightly around the galactic plane. Nearly every bright, familiar star visible on any clear night belongs to one of those two crowded layers, riding close to that same shared middle the sun itself rides near. Move higher, past both layers, and the crowd does not vanish outright. It simply thins, fast at first, and then more gradually, spreading out across far greater distances than anything the disk itself ever needed. Density, more than any hard boundary, is what actually separates a disk from whatever lies beyond it. Almost everything close and crowded stays low, near this shared plane. Almost everything higher grows rarer and quieter, each additional stretch of height holding a slightly sparser crowd than the one just below it. Layer folding gently into layer, rather than breaking off at any sharp edge. The whole disk, taken together, behaves less like a wall with a clear top and more like a slow, gradual fade. Not empty above, only patient, quieter and far less crowded than the two busy layers sitting underneath it, spread thin across a darkness with room enough for almost anything. Climb high enough past the thick, slow-turning disk, and a new shape begins to show itself. An enormous, dim, roughly rounded scattering of far older suns, spread loosely around the whole bright disk on every side at once. Astronomers call this outer region the halo, and unlike the flat, busy plane far below it, this shape holds no single favored direction at all. Stars out here drift on long paths of their own, rather than joining the disk's shared spin, each one keeping mostly to itself across enormous stretches of open space. Up here, the crowd has not thickened back up so much as changed its whole character, thin and ancient rather than dense and young. This older crowd owes nothing to the disk's shared rhythm below it, and none of it seems to mind. The change is real. Height alone does not empty a galaxy. It just replaces one crowd with a slower, older one. That halo is not small. Surveys put the stellar halo at somewhere around 300,000 light-years across, several times wider than the bright disk it loosely surrounds. This size belongs only to the halo built from stars, not to the far larger halo of unseen matter that some models stretch out even further beyond it. The two share a name, but not a size. Distances like these are hard to picture, and a single number rarely helps much on its own. Nothing marks a hard boundary out there. Even careful, well-funded survey teams still disagree by tens of thousands of light-years about exactly where the faintest edge finally gives out. Different surveys, using different tracer stars, sometimes push that faint edge outward by another 50,000 light-years or more. The stellar halo simply grows fainter and fainter with distance, thinning out until the last few stray stars fade quietly into the general dark, the way a coastline dissolves into fog rather than stopping at a line. Halo stars are also spread thin compared with the crowded disk below. A journey through the halo would cross enormous gaps between one star and the next, mostly through open, dark, empty space, rather than past any close neighbor. Density in the disk is measured in stars packed into modest volumes. Density in the halo is measured almost the opposite way, in how much nothing separates one lonely sun from another. A traveler moving slowly through this outer region could cross great stretches of it without ever passing near enough to a star to notice its light brighten. A few hundred cubic light-years of the crowded disk might hold a single star. The same stretch of the halo holds close to nothing at all. Astronomers sometimes call this kind of sparse population a stellar desert, more from habit than from any formal definition. The halo is honest about what it is, not a wall of stars, but a scattering, generous with distance and stingy with company. For a long time, the halo was pictured as a plain, evenly rounded ball, a tidy sphere sitting quietly around the disk. Newer maps, built from counting and tracking huge numbers of individual halo stars, suggest something less tidy, an elongated, tilted shape, closer to a rugby ball tumbling at an angle than to a smooth, round ball. That tilt does not line up neatly with the disk it surrounds, leaning instead at its own angle, shaped by however its stars first gathered and settled long ago. Mapping a shape this faint and this large takes patience. One star's position and one star's motion measured at a time, gathered slowly into a picture no single photograph could ever capture directly. That leaning, elongated shape now shows up consistently across several independent surveys, built using entirely different telescopes and entirely different methods. Earlier assumptions about a perfectly round halo mostly came from limited, small sample data rather than any deep physical reason. Shapes this faint rarely stay tidy on closer inspection, and the halo is no exception. Almost every star inside the halo is old, among the oldest known anywhere in the galaxy. Their light also carries a chemical signature of that age. Far less of the heavier elements found richly mixed into the young stars still forming inside the crowded disk below. Astronomers read that signature the way a tree's rings get read, each faint trace of iron or carbon marking how much material earlier generations of stars had cooked up and scattered before this one was born. A halo star formed with a thin chemical recipe, drawing on a galaxy that had not yet had time to enrich itself. Spectroscopy, the careful splitting of starlight into its component colors, is the tool that makes a signature this faint actually readable from Earth. No later stage of a star's life ever rewrites that early chemical signature in any meaningful way. That thinness never goes away once a star settles onto its long life. The recipe a star is born with is the recipe it keeps. The reason for that age gap is not mysterious once the timeline gets laid out. Halo stars mostly formed very early, while the galaxy itself was still a rough, half-settled cloud, long before the leftover gas had time to flatten down into the crowded, orderly disk that came later. Star formation back then was messier and less organized than it is inside today's tidy spiral arms, scattered across whatever clumps of gas happened to be dense enough to collapse. By the time the disk finally settled into its familiar flat shape, most of the stars that would become the halo had long since finished forming, locked into their own separate paths above and around the flattening cloud below them. Whatever gas the young galaxy did have on hand back then was still mostly plain hydrogen and helium, only lightly seasoned with anything heavier. Age, in this sense, is really just a record of timing. The halo formed first, and the disk came together only after. Scattered through this halo sit roughly 150 dense knots of stars, known as globular clusters. Each one a crowded, gravity-bound gathering that can hold anywhere from tens of thousands of stars to over 1 million packed into a comparatively small volume. Seen through even a modest telescope, a single cluster looks less like a scatter of individual points and more like a single glowing smudge, its member stars too close together to pick apart one by one near the crowded center. Every one of these clusters formed as a unit, born together from the same collapsing knot of gas, rather than gathering gradually, star by star, over time. That shared birth is part of what keeps them so tightly bound together, even now, billions of years later, still orbiting as one coherent group, rather than drifting apart into the wider halo around them. Each cluster still keeps to its own long private orbit around the galaxy's distant center, largely undisturbed by whatever happens to be going on inside the busy disk far below it. Only 150 are confirmed so far. A few more may still be hiding directly behind the crowded disk, out of easy view from Earth. Globular clusters rank among the oldest structures anywhere in the galaxy. Some of them formed so early that their age comes close to the age of the universe itself. Astronomers estimate that age by studying the stars still burning inside each cluster, since the dimmest, coolest, longest-lived stars in any group reveal roughly how much time has passed since the whole cluster first came together. A cluster this old has outlived the Sun many times over in relative terms, forming while the galaxy itself was still assembling its earliest pieces.
Nothing about a cluster this ancient looks fragile up close. If anything, the tight grip of gravity that first bound its stars together has only grown stronger with time, pulling stragglers back in rather than letting the group drift apart. Few objects found anywhere nearby carry quite this much unbroken history bound together into one single, tightly packed structure. Old enough to remember the universe's own childhood, this knot of stars still burns quietly in the dark, indifferent to how much time has passed since. Disk stars mostly keep to neat, nearly flat, nearly circular paths, rarely wandering far from the crowded plane they were born into. Globular clusters do nothing of the sort. Each one follows a long, looping orbit tilted at its own particular angle to the galactic plane, some swinging high above it, others plunging deep below, with very little agreement between one cluster's path and the next. A single cluster can spend a large stretch of its orbit far outside the familiar disk entirely, only sweeping back through the crowded middle briefly before curving away again into quieter space. Watching a cluster's path traced out over millions of years would look less like the tidy loop of a planet and more like a slow, wide arc drawn by something that never checked which way was supposed to be up. A planet's orbit, traced out year after year, looks almost embarrassingly tidy set beside a path like this one. Order, out here, was clearly never part of the plan. That tilted, disorganized wandering is itself a kind of evidence, a fingerprint left behind by how and when these clusters formed. Globular clusters came together before the galaxy had finished flattening itself into the tidy disk seen today, so they never had the chance to settle into the shared, orderly plane that formed only afterward. A star born inside today's disk inherits a flat, cooperative orbit almost automatically, shaped by the crowd of material it formed alongside. A cluster born earlier, before that crowd had organized itself, inherited no such discipline, and it never gained any later either. That particular tilt appears to have been set very early on, and observations so far suggest it has barely shifted since. No amount of time spent near the disk seems able to reset that original tilt. Watching where a cluster's orbit points is, in a real sense, watching a clock stopped at the moment the cluster was born, still ticking through its old, tilted path, long after the disk around it grew calm and flat. Some globular clusters barely interact with the crowded disk at all across an entire orbit. They spend the overwhelming majority of their long, slow circuit out in the quiet halo, only grazing the busy plane for a comparatively short stretch before swinging back out again into open space. A cluster like this could complete most of its journey without ever coming close enough to the Sun's own neighborhood to register as more than a distant smudge. Passing through the disk briefly does carry some risk. The crowded middle pulls harder and less evenly than the open halo does, tugging gently at a cluster's outer stars each time it sweeps through. A brief, glancing crossing rarely leaves any lasting mark on a structure built this loosely to begin with. The pull barely registers against an orbit this wide, spanning a huge stretch of the halo to begin with. Most clusters shrug it off and continue on, drifting back out to the same slow, wide, largely undisturbed path they have followed for billions of years. None of this makes the halo empty space with a name attached to it. It is, instead, a separate structure sitting alongside the disk rather than simply above and below it. Poor in stars compared with the crowd packed into the plane, but older than almost everything inside that tight, busy plane it surrounds. The disk gets the spiral arms, the star-forming clouds, the crowded traffic of orbits circling in step with one another. The halo gets almost none of that, and keeps instead something quieter and rarer, a kind of seniority, an old, scattered claim on space that stretches out far past where the disk's own busy crowd finally runs thin. That seniority stays quiet, but careful counting finds it in nearly every star measured across the whole halo. Scattered among the old, slow-moving stars of the halo is a much rarer kind of traveler, a star moving so fast that gravity alone can no longer bend its path into any ordinary orbit. Most stars, wherever they sit in the halo or the disk, circle the galaxy on some kind of closed, repeating loop, returning again and again to roughly the same regions over immense stretches of time. This rarer kind does not. It moves on a path closer to a straight line than a loop, carrying it further and further from the galaxy's center with each passing age rather than swinging back around. Spotting one takes careful, patient measurement, since a fast star hides among millions of ordinary ones unless its motion gets tracked precisely enough to stand out. No telescope tuned only for ordinary starlight would ever flag a star moving quite this unusually fast. Most of the halo moves slowly and calmly, and only a small handful moves as though it has somewhere else entirely to be. Astronomers give these rare, fast travelers two related names: hypervelocity stars for the most extreme cases, runaway stars for a somewhat broader and slightly gentler category. Both groups share the same basic trait: motion too fast for the galaxy's gravity to ever pull them back into a normal, circling path. The fastest examples move quickly enough that, given enough time, no amount of gravity left in the galaxy will ever be strong enough to bring them home again. Slower runaways may still loop back eventually, tracing out an enormous, stretched arc before gravity finally wins and reverses their outward drift. Naming them at all took decades of increasingly careful measurement, since a star's true speed only reveals itself once its motion across the sky and its motion toward or away from us both get measured with real precision. Neither label is technically wrong. The two terms simply describe overlapping ends of the very same underlying phenomenon. Stars fast enough to leave for good are rare, and finding one always feels a little like spotting a single spark thrown clear of a much slower fire. One especially well-studied case moves at more than 1,700 kilometers every second, among the fastest stellar speeds ever measured directly. At that speed, covering the entire distance between the Earth and the Sun would take less than a day and a half, a gap that ordinarily takes light itself over 8 minutes to cross. Astronomers using the Gaia Space Telescope tracked this star's position and motion precisely enough to reconstruct not just its current speed, but a rough sketch of where it must have started from. That reconstruction points back toward the crowded, violent region near the galaxy's very center, hinting strongly at how a star ever reaches speeds like this in the first place. A star moving that quickly does not slow down gradually the way a thrown ball does. It simply keeps going, carrying that same tremendous speed outward for as long as anything remains nearby to measure it. Its precise birthplace can never be confirmed directly from here, only carefully inferred from the shape of its current path. Some journeys, once begun this fast, never really finish. Most hypervelocity stars appear to trace back to one particular kind of violent close encounter, an approach near the supermassive black hole sitting at the galaxy's very center. A pair of stars orbiting each other closely can wander too near that black hole's immense gravity, and when that happens, one star of the pair sometimes gets captured or destroyed, while the other gets flung outward at extraordinary speed.
The whole process plays out gently by cosmic standards, a slow gravitational sorting rather than any kind of explosion, even though the result is a star suddenly moving faster than almost anything else nearby. Only a very close approach produces this effect. Stars passing at any reasonable distance from the black hole feel barely any different pull than stars passing near any other massive object. The mechanism sounds dramatic in outline. Only the very closest possible approach to that black hole ever produces an ejection quite this dramatic. The outcome plays out in near total silence and stillness. A single star, gaining a speed most others in the galaxy will never reach. A second, gentler mechanism also seems to produce runaway stars, one that starts inside a close binary system rather than near any black hole. Two stars can spend most of their lives orbiting tightly around each other, bound together by mutual gravity for millions or billions of years at a stretch. If the heavier of the pair explodes as a supernova, its sudden loss of mass can loosen or completely break the gravitational grip holding the pair together. The surviving star, no longer held by its former partner, continues moving outward at whatever speed it happened to be circling at the moment of the explosion, now traveling in a straight rather than a curved path. No black hole needs to be anywhere nearby for this version of the story to unfold. An explosion this violent needs no dramatic aftermath of its own to still send one lone star flying for good. One partnership ends suddenly, and its surviving half simply keeps moving in whatever direction it happened to be heading at that final instant. Once a star gets launched this way, it settles into a long, largely straight path that can carry it far above or far below the galaxy's crowded plane. That path never curves back sharply the way a planet's orbit does. Gravity still tugs at the star the whole way, but far too weakly at these speeds to bend the path into anything resembling a loop. Over enough time, that straight path lifts the star clear out of the busy disk entirely, into the same open, sparsely populated region the halo occupies. A runaway star crossing that boundary does not notice any change. There is no wall, no line, nothing marking the moment it leaves the crowd behind. That straight course holds for as long as the star itself exists, whether anyone happens to be watching or not. Predicting exactly where such a star will end up centuries from now remains genuinely difficult. From the ground, tracking such a star means watching one point of light slowly, steadily separate itself from everything gravity still holds close nearby. A hypervelocity star, flying high above the disk, passes through territory almost entirely empty of other stars. No spiral arm crowds the view, no cluster of nearby neighbors, nothing but the same thin, patient scattering found everywhere else across the halo. Where the disk offers close company at every turn, star after star within easy reach of a telescope, the region above it offers mostly distance, one lonely traveler moving through a landscape built almost entirely out of empty space. That contrast is part of what makes these stars worth cracking in the first place. A fast star crossing a crowded region barely stands out, but a fast star crossing near total emptiness is, for long stretches, the only thing moving at all. A telescope scanning that same stretch of sky on an ordinary night mostly finds nothing worth logging at all. Loneliness up here is simply the ordinary condition, and a hypervelocity star only makes that ordinary emptiness a little more visible, for as long as it happens to be passing through. Modern surveys have made stars like these far easier to find than they once were. The Gaia Space Telescope, built specifically to measure the positions and motions of well over 1 billion stars with extraordinary precision, has turned up dozens of strong candidates for hypervelocity and runaway stars scattered across the outer galaxy. Before a mission like this existed, spotting even one such star required years of painstaking, targeted observation. A single confirmed case treated almost as a rare discovery in its own right. Now researchers can sift through a vast, uniform catalogue instead, comparing millions of measured motions at once to flag the handful moving fast enough and in the right direction to qualify. Some candidates later prove to be ordinary stars measured imperfectly and get dropped from the list after closer study. Earlier catalogues, built painstakingly one star at a time, never came anywhere close to matching this scale of coverage. The confirmed count keeps climbing anyway, one careful measurement at a time, filling in a map of fast travelers that barely existed at all only a couple of decades ago. Given enough time, a sufficiently fast runaway star eventually reaches a kind of boundary. Not a physical wall, but the point at which the galaxy's gravity simply cannot pull hard enough to hold it any longer. Past that point, the star is no longer bound to the galaxy at all, even loosely. It continues drifting outward into the vast space between galaxies, carrying its own light along with it, into territory almost nothing else nearby ever visits. No ceremony marks that crossing, and no instrument watching from nearby would see anything change in the star itself at the exact moment it happens. What changes is only the outcome, stretched out far into the future. A star that once belonged, however loosely, to one particular galaxy slowly becomes a star belonging to none. Few objects manage to leave a whole galaxy behind. The star itself never notices the exact moment its old galactic home finally lets it go for good. Fewer still do it this quietly. Stars like these are the closest real answer to a simple, honest question. What is actually sitting directly above the solar system right now at this exact moment? Not some solid object waiting to be discovered, and not simply empty dark stretching on forever without end. Somewhere out there, at any given time, a handful of these rare, fast, solitary stars are crossing that same general territory. Each one many light years from its nearest neighbor, each one following its own straight, private path through the halo's wide, thin scatter of old light. None of them are heading anywhere near the solar system itself, and none of them ever will. Empty is not quite the right word for a stretch of space still holding the occasional lone traveler. They simply share the same general kind of space, far above the crowded plane, moving through it the same way the whole halo does, slowly, sparsely, and almost entirely alone. Far above and far below the crowded center of the galaxy, not near the sun's own quiet neighborhood, but directly over the galaxy's own dense core, sit two enormous structures, too faint for any human eye to ever notice on its own. An ordinary photograph of the night sky shows no trace of them, no matter how dark the surrounding conditions. Their presence changes the picture of what actually rises above a galaxy's crowded plane, adding something far larger and far stranger than any single star or cluster ever could. Their exact origin is still debated among researchers studying them closely. What is not in doubt is that they are real, mapped repeatedly across years of careful observation. These two structures carry the name Fermi bubbles, after the space telescope that first revealed them clearly. Each one is a colossal lobe of extremely hot, thin gas, ballooning slowly outward from the very center of the galaxy, one rising above the crowded plain and the other sinking an equal distance below it. Together, they form a matched pair, roughly mirrored across the plane the way a shadow mirrors whatever casts it, each lobe reaching out into the quiet space beyond the disk. Neither lobe touches the sun's own neighborhood even loosely. Both sit centered squarely over the galaxy's dense core instead, far closer to the black hole at the center than to anything nearby us. Their paired, mirrored shape looks anything but accidental once the whole structure gets mapped out in full. Bubbles this size, rising directly out of a galaxy's own crowded heart, are not something every galaxy shows so plainly, if it shows any at all.
Each bubble reaches roughly 25,000 light-years out from the galactic plane, a genuinely enormous distance, measured against almost anything else nearby the solar system. Stacked together, the pair spans something close to 50,000 light-years, from the very bottom of the lower lobe to the very top of the upper one, directly above and below the galaxy's crowded core. That height dwarfs the disk itself in one particular direction, even though the disk still holds vastly more mass and vastly more stars packed within its own much flatter shape. A structure this large took a genuinely powerful event to produce, since ordinary, gentle processes rarely manage to push gas this far from a galaxy's center in any organized shape. A single number like that rarely conveys just how much genuinely empty space such a height actually spans. Picture instead two quiet towers of thin, hot gas, each one rising many times higher than the whole disk is thick. Nobody noticed these bubbles at all until the year 2010, when researchers, sifting carefully through years of data gathered by the Fermi Gamma Ray Space Telescope, spotted a faint, consistent pattern nobody had picked out before. The telescope itself was not built to hunt for anything shaped quite like this. It was designed more broadly to map high-energy light pouring in from every direction across the sky. Only after combining years of accumulated measurements did the bubble-shaped pattern become clear enough to describe with any confidence, emerging gradually out of what had looked, at first glance, like ordinary background noise. A structure spanning 50,000 light-years had been sitting directly above and below the galactic center the entire time, invisible not because it was hidden, but because nobody had yet looked in exactly the right way. Patterns hidden this deep in a dataset rarely announce themselves clearly all at once. Sometimes the largest things nearby are also the easiest to overlook. Fermi bubbles glow almost entirely in gamma rays and X-rays, forms of light that sit far beyond anything the human eye or an ordinary camera was ever built to register. Visible light, the narrow sliver of the whole spectrum eyes evolved to use, simply does not carry much information about structures like these at all. That mismatch explains a good part of why something this enormous went unnoticed for so long. The bubbles were never truly invisible, only invisible to the one narrow kind of light most instruments and most eyes happen to rely on. Specialized detectors built to catch gamma rays directly had to exist first, before anyone could even begin looking for a pattern like this one. A wider slice of the electromagnetic spectrum was the missing piece all along. Ordinary optical telescopes, no matter how large their mirrors, simply are not built to catch light of this kind. Once the right instrument finally pointed in the right direction, the bubbles proved to be one of the most obvious large-scale structures in the whole sky. Producing a pair of structures this size took an extraordinary amount of energy, something on the rough order of 100,000 ordinary supernova explosions, all releasing their energy at once,
rather than scattered gradually across billions of years. A single supernova outshines an entire galaxy briefly while it happens. Multiplying that by 100,000 gives some sense of scale for whatever event first inflated these bubbles outward. Nothing gentle produces a number like that. Whatever process powered this outburst had to draw on some of the most energetic sources known to exist inside any galaxy, concentrated tightly around the crowded, violent region at the very center. Few events anywhere in an otherwise quiet galaxy's history come close to matching that total output.
Numbers this large rarely map cleanly onto everyday intuition, and this one does not either. It simply marks the difference between an ordinary, quiet galaxy and one that, at some point in its history, briefly did something far from ordinary. Most researchers trace the bubbles back to one of two related possible causes, both centered on the same violent neighborhood near the galaxy's core. One idea points to a sudden outburst from the supermassive black hole sitting there, a brief but powerful flare of activity as infalling material released a huge burst of energy on its way inward. A second idea points instead to an intense, sudden burst of star formation in that same crowded region, with many stars forming and exploding in relatively quick succession, adding up to a comparable total release of energy. Either explanation would need the event to have happened somewhere within roughly the last several million years, recent enough by galactic standards for the bubbles to still be expanding rather than having faded away entirely. Researchers have not yet settled definitively on one explanation over the other. Neither competing idea has yet been ruled out by any observation gathered so far. Both remain live possibilities, tested against every new observation as it comes in. However the bubbles first formed, their position leaves little room for doubt about where the responsible event took place. Both lobes sit almost exactly astride the galaxy's dense core, one over it and one under it, not over the comparatively quiet neighborhood the Sun occupies. The Sun sits far out toward the rim of that same disk, a long way from the crowded, violent middle where the bubbles originate. Standing anywhere near the Sun and looking up offers no view of either bubble at all. Not because the crowded plane hides them, but because their light arrives in a form no eye was ever built to catch. All that height, and not one sign of it visible from here. Recent, more detailed observations have turned up something unexpected tucked inside these otherwise blazing hot bubbles. Small pockets of surprisingly cold gas, drifting through a structure that most existing models describe as far too turbulent and far too energetic for anything that cold to survive intact. Finding cold material inside a structure powered by energy on this scale raised real questions about exactly how the bubbles are put together internally, since a smooth, uniformly hot balloon of gas was the simpler picture researchers had generally expected. One possibility is that these cold clumps represent leftover material swept up from the surrounding galaxy, dragged along rather than heated fully by whatever process inflated the bubbles around them. Confirming details like these takes extremely sensitive instruments, capable of picking apart temperature differences across a structure this faint and this far away. Cold and hot rarely share space this comfortably for long. The biggest, hottest structures nearby, it seems, can still be hiding a few quieter pockets deep inside them. Whatever explanation for their origin eventually wins out among researchers, the Fermi bubbles remain among the largest structures known to rise directly out of the galactic plane in either direction. They stand as proof that what waits above and below a galaxy's crowded disk is not limited to stars, star clusters, or the halo's own thin scattering of old light. Sometimes what rises is instead something built almost entirely out of energy itself, glowing not with starlight, but with radiation far outside anything an eye could ever see directly. A galaxy, seen only in visible light, would never reveal a structure like this at all, no matter how carefully or how long anyone happened to look at it that way. No smaller structure nearby matches that same enormous reach. Above that same busy core, two silent towers of energy have been standing, slowly, for millions of years, waiting for the right kind of eye to finally notice them. From any point inside the thin disk, including the exact spot the Sun occupies, the crowded galactic plane does not sit off in one particular direction the way a mountain range or a distant coastline might. It wraps entirely around, circling the whole sky at once, rather than occupying just one patch of it. Standing anywhere inside the disk and turning slowly in a full circle would keep that same crowded band in view the entire way around, never disappearing off to one side, the way a single landmark eventually would. That completeness comes directly from being inside the structure rather than outside it, embedded within the same flat sheet of stars and gas that makes up the plane itself. That circle in the sky never breaks, no matter which direction anyone turns to face. This kind of view is simply what living inside something flat and enormous looks like from underneath, or rather, from within. That full circle wrap is exactly why the Milky Way looks from Earth like a pale, faintly glowing band stretching across the whole night sky, rather than anything resembling a spiral or a pinwheel shape. A spiral shape only becomes visible from outside a disk, looking down or up across its whole flat face at once, the way a photograph of another galaxy typically shows it. From inside that same disk, all that same spiral structure gets flattened by perspective into a single long strip. Its separate arms and gaps merge together into one continuous glow running around the sky. Anyone picturing the Milky Way as a spiral is picturing a view no human eye has ever actually had. No single point along that pale band looks meaningfully different from its neighbors to an untrained eye. What every human eye has actually seen, instead, is this quiet, pale band circling overhead night after night in every culture across the whole of human history. Seeing the Milky Way the way it appears in illustrations, laid out flat with its arms curling outward from a bright center, would require actually leaving the disk behind and looking back down, or up, along a steep angle far removed from the crowded plane itself. Only from that kind of distant, tilted vantage point does the spiral shape stop being flattened by perspective and start showing its true, layered structure clearly. No comfortable middle ground exists between the two views. A small step away from the plane barely changes the picture at all, and only a genuinely large, steep departure eventually reveals anything resembling the familiar spiral shape. Every photograph anyone has ever seen of a spiral galaxy that is not our own required exactly this kind of distant, angled vantage point to capture. Distance, in this one particular respect, really is the only thing that changes the whole picture. Our own galaxy has never been photographed that way, and the reason has nothing to do with technology and everything to do with geometry. No spacecraft and no telescope of any kind has ever traveled far enough beyond the disk to turn around and photograph the Milky Way's own spiral shape directly from outside it. Every familiar image labeled as a picture of the Milky Way's spiral arms is, in fact, a reconstruction, carefully built from measuring the positions, distances, and motions of enormous numbers of individual stars and clouds of gas, rather than captured directly in a single photograph.
Researchers piece that reconstruction together the way a detective pieces together a scene from scattered clues, combining thousands of separate measurements into one coherent picture nobody has ever actually seen with their own eyes. The general shape those reconstructions describe is trusted, tested, and refined constantly against new data as it comes in. Every one of those familiar images required decades of patient, entirely indirect measurement to finally assemble.
Custard is not the same as photographed, and for the Milky Way's own full spiral shape, it may never be the same thing at all. Looking along the crowded plane toward the galactic center means looking straight through an enormous thickness of dust and gas. Far more of both than a view in almost any other direction ever has to pass through. That thickness peaks exactly where the thin disk itself is most tightly packed, right along the same crowded band responsible for the pale strip visible across the night sky. Dust grains this small individually block very little light on their own, but stacked across tens of thousands of light years, their combined effect becomes overwhelming. A view toward the center is a view through the single dustiest, most obstructed stretch of sky available anywhere from where the solar system sits. That thickness barely changes at all from one year to the next. That obstruction is neither unusual nor rare. Anything that lives deep inside a flat, dusty structure and tries to look straight through the middle gets exactly this. That dust dims the direct visible light arriving from the galaxy's own center by roughly 25 stellar magnitudes, a number astronomers use to measure how much fainter one light source appears compared with another. Translated into a simpler comparison, that dimming works out to something close to a factor of 10 billion, reducing whatever visible light originally left the center down to a whisper by the time even a trace of it reaches Earth. A dimming factor that large is difficult to picture in ordinary terms. It is roughly the same kind of gap separating a single lit match from the combined output of an entire well-lit city. Even the brightest possible source sitting at the galaxy's center could never punch through that much intervening dust using visible light alone. Numbers this extreme rarely mean much of anything until translated into something more ordinary and familiar. What gets lost along the way does not vanish entirely, but by the time it would reach any telescope built to see ordinary color, there is nothing left worth measuring. Because of that same dust, the galaxy's actual center remains completely invisible to an ordinary eye and to an ordinary telescope alike, no matter how large the mirror or how long the exposure runs. Visible light simply never survives the trip, absorbed and scattered away by dust long before it could ever reach any detector built to register that particular kind of light. This is the exact same crowded plane responsible for the pale band circling the whole sky. The dust that hides the center and the dust that produces the band are, in the end, one and the same material, viewed from two different angles. A visitor relying only on ordinary eyesight could study the night sky for an entire lifetime without ever once glimpsing that crowded heart directly. That hidden heart has never once been seen directly by anyone at any wavelength the bare eye can register. The center has been sitting there the whole time, hidden in plain sight, behind the very glow it helped create. To study that hidden center at all, astronomers rely instead on infrared and radio wavelengths, forms of light with much longer wavelengths than anything visible to an eye. Those longer waves slip through the same dust that blocks ordinary visible light almost completely, passing between and around individual dust grains far more easily than shorter, more easily scattered visible light ever can. Telescopes tuned to these longer wavelengths have mapped stars, gas, and even the supermassive black hole sitting at the very center
in remarkable detail, despite that whole region staying permanently invisible to direct observation. Switching wavelengths, in effect, is less like turning up a light and more like switching to an entirely different sense altogether, one built to notice exactly what visible light cannot. Longer waves barely notice a little dust sitting in the way. Radio dishes and infrared cameras do most of that particular work today. What ordinary eyes will never see directly, careful instruments tuned to a different kind of light have mapped in patient, painstaking detail. Looking straight up, away from the crowded plane entirely, avoids nearly all of that same obstructing dust, offering by far the clearest view available from anywhere inside the disk. Dust concentrates overwhelmingly close to the plane itself, thinning out rapidly with height, the same way haze near the ground thins out gradually with altitude on an ordinary hazy day. A view straight up passes through only a comparatively thin slice of that dust before reaching open space. Compared with the enormous thickness a view along the plane has to push through instead. This is the same basic reason astronomers studying distant galaxies beyond our own often prefer to look through our galaxy's poles rather than along its crowded plane, avoiding as much local dust and confusion as possible. That clear view took no special arrangement to produce. Even professional sky surveys favor this same clear direction when hunting for anything faint and distant. Straight up remains the one direction inside this whole flat, dusty structure that stays reliably, consistently clear. The pale band circling the sky and the galaxy's hidden, invisible center are, at bottom, one single truth described twice over, seen from two slightly different angles. Living inside a flat, dusty disk means a clear, open view straight up and a heavily clouded, dust-choked view along the crowded plane, exactly where nearly all of the galaxy's stars and dust actually sit concentrated together. One direction offers almost nothing to block the view. The other offers almost everything worth seeing, buried behind material too thick to see through directly. Neither half of that description is really separate from the other. Each one only exists because of the same flat, crowded shape responsible for both. Both halves of that quiet trade happen at once, every single night, without exception. No third option exists for an observer standing anywhere inside a disk built quite this flat. Flat galaxies give with one hand and take away with the other, and both hands, it happens, are doing exactly the same job. Almost every spacecraft ever launched from Earth toward the outer solar system and beyond has flown roughly within the shared plane the planets travel in, rather than straight up toward the galaxy's own distant pole. That path makes practical sense long before it makes any kind of cosmic sense. Nearly every planet, moon, and useful gravitational assist a mission might rely on for a boost along the way sits close to that same flat plane, making it by far the most efficient direction to travel. Climbing steeply away from that shared plane costs an enormous amount of extra fuel for very little practical benefit to any mission studying the planets themselves. Every probe that has ever passed by Jupiter, Saturn, or any planet farther out has done so by staying close to this same shared, familiar plane rather than climbing away from it. None of that was ever really about the galaxy at all. One probe, Ulysses, was aimed deliberately out of that plane instead, ending up tilted some 79 degrees away from the flat sheet the planets keep. The plane it left, though, was the small one, the planet's own. The galaxy's far larger plane was never the one being measured against. Fuel budgets,
far more than curiosity about the galaxy itself, decided almost every one of these chosen routes. This was always about the far closer, far more practical business of visiting the planets in the first place. Voyager 1, the most distant human-made object ever launched, now travels at an angle of roughly 35 degrees above the plane the planets share. A real and measurable climb, rather than no climb at all. That angle came from a close flyby of Titan, Saturn's largest moon, which bent the spacecraft's path sharply northward on its way further out into the solar system. 35 degrees sounds like a considerable tilt, and by the standards of a spacecraft built to study planets, it genuinely is. Compared with the steep angle separating that shared plane from the far larger one the galaxy itself keeps, though, that same climb still covers only a modest fraction of the full distance. Nothing launched since has ridden that far north of the plane on its way out. Every additional degree of tilt like that one had to be paid for entirely by chance, not by design. Voyager 1 now rides further north of that same plane than anything else humanity has launched, and it is still, by that far larger measure, barely off the ground. Pioneer 10 and Pioneer 11, launched slightly earlier than Voyager, stayed even closer to that same shared plane on their own way out of the solar system. One heads roughly against the direction the Sun itself moves through the wider galaxy. The other heads roughly along with that same motion. The two probes drifting apart from each other in opposite general directions over the decades since launch. Neither one was ever aimed even approximately out of the galactic disk, since neither mission had any reason to attempt to climb that steep. Their instruments were built to study planets, particle environments, and the outer reaches of the Sun's influence, not to chart any kind of path out of the galaxy itself. Both probes stopped transmitting years ago, though their long paths continue regardless, carrying no one and nothing new to report. Both probes, silent now, continue drifting outward at their own steady pace, still close to the same flat plane they followed from the very start. No spacecraft ever built by humanity carries anywhere near enough fuel to climb out of the plane of the planets at an angle that meaningfully closes the gap toward the galaxy's own separate plane, let alone actually reach or cross it. The fuel required for a climb that steep dwarfs anything any current rocket or propulsion system could practically carry, launch, and still have left over for the instruments actually doing the science. Engineers planning any real mission choose paths that work with that same plane rather than fighting against it, using gravity assists that only function efficiently within that same shared, flat arrangement. Climbing toward the galaxy's plane instead of working within the solar system's plane would mean giving up nearly every efficient trick spacecraft engineering currently relies on. That much fuel simply does not exist yet. Fuel, not ambition, is what sets the ceiling here, and no fuel of that size has ever been loaded onto anything. Even the boldest realistic departure from the shared plane of the planets still leaves a spacecraft deep inside the thin disk, nowhere close to breaking free of it entirely. A climb of that kind, impressive as it is by the standards of solar system exploration, barely registers against the disk that itself stretches roughly 1,000 light-years from top to bottom. Whatever spacecraft manages the steepest climb yet remains just another small object, drifting among the same crowded band of stars, dust and gas that fills the whole thin disk around it. Leaving that plane, however cleanly executed, comes nowhere close to leaving the galaxy's much larger structure behind. The thin disk barely notices one more small visitor passing through it. Scale is the whole problem here, not effort or ambition.
However far it travels by human standards, a tiny machine like this is still standing on the same crowded floor as everything else nearby, just at a slightly different angle.
A quiet difference runs through this entire comparison. Easy to miss without laying the two climbs side by side directly. Leaving the plane of the planets belonging to the solar system is a modest, almost ordinary maneuver, one achieved by a modest handful of relatively small spacecraft using little beyond a well-timed gravitational assist. Leaving the galaxy's own separate plane, clearing both the thin disk and the thicker one wrapped around it, is a distance no human-built object has ever approached, not even remotely, using any technology currently available. One kind of departure has become almost routine, carried out again and again without much fanfare. The other remains, for now, entirely theoretical, absent from even the most ambitious mission proposals on any drawing board today. That asymmetry is not treated as urgent by anyone currently planning a mission. Nothing on the horizon changes that gap anytime soon. Tonight's route climbs slowly through exactly this difference, one steady step at a time. It began down in the shared flat plane where the planets travel, then rose through the steep tilt separating that small plane from the galaxy's own much larger one, up into the crowded, star-forming thin disk and the older, puffier, thick disk wrapped loosely around it. Past the sun's own quiet position, riding just off the crowded middle of it all. From there, the climb continued out into the old, sparse halo, past a rare, solitary star flying its own straight path far from any neighbor. Above the enormous, silent bubbles rising from the galaxy's own crowded heart. And back down again, through the dust that turns this whole galaxy into a pale band across the sky, rather than a visible spiral. That climb was never rushed, and it never skipped a single layer. Every step of that climb, from the first tilted planet to the last dusty view toward the center, has been building toward the same quiet answer. Nothing along that whole long climb ever really came close. The disk thins out gradually, rather than stopping at any clean edge. The halo stretches on for hundreds of thousands of light years past even that, and any direction anyone might call up eventually leads only to more open, patient, unhurried dark. The solar system sits where it has always sat, tucked inside the flat, crowded disk of a single, ordinary galaxy among countless others, and there is nowhere close by left to climb toward instead. Let that be the last quiet thought before sleep tonight. Up and out of a solar system is possible, gently, with the right sort of push. But up and out of a galaxy is not. Not for us. Not yet. Maybe not ever. None of that distance was ever a flaw. It is simply how galaxies are built. Rest easy inside that flat, quiet disk, breathing slowly, held gently in place by nothing but gravity and time. Exactly where a small, patient world like this one has always belonged.